Hello everyone, thank you very much for watching the recording of my presentation. My name is Rodrigo Duran, and today I'm going to be talking to you about risk-aware optimal stopping via gradient-boosted quantile regression. To provide a bit of an introduction, optimal stopping is the problem of choosing a time to take an action based on sequentially observed random variables to maximize or minimize an expected reward or cost. An example of this is the pricing of American options, where regression-based algorithms such as the least square Monte Carlo methods are used. In recent years, machine learning approaches have sought to enhance this regression-based approach. Examples of this include deep learning approaches as well as randomized neural networks. This project explores a gradient-boosted regression approach to the pricing of American options. To provide some background on optimal stopping, you can think about the price xt at a time t of an asset that varies according to a stochastic differential equation. Now, the behavior of this asset up to a time up to the present t is known, but because of the uncertainties in the system, we can never be for sure at the time of sale if the choice of time is the best. Again, the choice of time here being the degree of freedom that we have. We only get to say when to stop. As given this, a stopping strategy that gives the best result in the long run is therefore what is desired and what we're after. Now, in order for this to work, we have to think about it in the form of an Ito diffusion. So a time homogeneous Ito diffusion is a stochastic process, x of t, where there is the time t and there is a particle, and this is a mapping between the time and the omega field to the real line and to the n dimension, and this satisfies the stochastic differential equation, which some of us have seen before, where you have your deterministic behavior and you also have your diffusion term. Now, b of t, as I mentioned before, that is the m-dimensional Brownian motion, which in respect of its own mapping, which is on this diffusion term, and this satisfies the conditions of being Lipschitz continuous. That means that rate of change is bounded and well-defined. Now, another property of Ito diffusions is the strong Markov property, and that is, if we think of a set n of t of an increasing families of sigma algebras that are themselves a subset of omega, we have a function tau, which is a mapping between that omega and the real line, and this is called a strict stopping time with respect to n of t if for a particle omega that is the input of this mapping, less of t, it happens to be contained within that set for all the times that are greater or equal to 0. If in addition to that, we have a function f that is a bounded Borel function on the real and dimensional, then tau is considered a stopping time with respect to the filtration for a value tau that is less than infinity almost surely, so this value exists. Then we have the commonly known and sort of like what we're used to for the Markov property, where the expectation depends only of the value of the current state at that time. So in a sense, combining all of these concepts together, the optimal stopping problem, we have that the x of t, we define that as an Ito diffusion for all reals on the n dimension, and we define g to be the reward function. Now, for this specific definition, g, whatever input we have, has to be greater than or equal to 0. There are ways to formulate this as a cost function as opposed to a reward function, and without changing too much of the properties. They're actually very flexible. But the reward function has to be continuous. So if we think about this as the objective of our problem, to find an optimal stopping tau, so tau asterisk or tau star, then for the given stochastic process that we have that the optimal reward function is the expectation, the computation of the expectation for the value of our stochastic differential equation at a time tau over all the supremum over all the tau. So out of all the stopping times that I have, which one yields the most optimal sort of like reward value or minimizes the cost value, all depending on how this process is set up. Now, something that is very important for all of these different approaches is the Euler-Maruyama method this given because depending on the differential equation that we have, some of them have a very well-defined solution. In this case, this was not particularly needed for the example that I implemented, but for some differential equation, in order for us to propagate forward in time, we have to understand how to discretize our solution, how to basically do like a finite different approximation of our propagation forward in time. And that's what the Euler-Maruyama method allows us to do. So, ensemble method, this is the core of this presentation. The ensembles method combines prediction of several base estimators built with a given learning algorithm in order to improve robustness over a single estimator. I do not have like a background or how the math behind this works, but scikit-learn has a very good article on that, as well as Wikipedia, that provide all of the math and all of the different approaches. Now, for this specific project, we implemented the gradient boosted tree as the ensembles method, given its popularity as both a regression and classification approach, particularly for tabular data, which is sort of like what we're dealing here. We have data that is sorted depending on the time. Now, for the results, I have a specific section here where I'm using the mean square error. For the gradient boosted approach, you can modify the objective that you want to use. And because the traditional approach for the least square Monte Carlo does a regression on the expectation, that is what we want to accomplish here by using a mean square error as our objective. So how different is it for, in this case, if you look at the bottom, the least square Monte Carlo approach by Longstan and Schwartz, that is the seminal paper, considered the article that started it all, or one of the articles that was very fundamental. And we can see that for the simulation results, given the same parameters, we obtain values that are very close as far as the optimal time to do. I believe in this case, this is a put option for the American pricing. I am not too familiar with the finance terminology. But if I go ahead and I move to the plot, I can see sort of like the behavior of, I believe this is about 10 to 15 trajectories. I think it's like 10 trajectories. And you can see all of the different stopping times. Now, there are about, if I remember correctly, there are about 15 opportunities to stop. This is across 1 year. So there are 15 points in which across the year we can say, yes, go ahead and buy or sell. And this, I believe there were like about 1,000 or 2,000 trajectories in total. But we can see that most of them, they're all the different points in which they decide to stop. So that is basically for each of the trajectories. Very similar behavior to what was presented in that article that we use as a reference. Now, for quantile regression, there is the option to take the objective for the gradient boosted and use different formulations of the cost function, or the function that we use as a metric to do the training. And one of those is a quantile loss. It's a quantile regression. And what is interesting about this is the idea here being, well, can I modify that alpha? Can I modify that value that tells me which quantile I want to sort of like shoot for in the pinball, I believe it's called the pinball loss function, to say, hey, what if I were to do it in this case, alpha equals to 0.5, that will be the median. What if I regress towards the median? What if I regress towards like the left of the median or the right of the median? Will that be something similar to do a risk neutral or risk seeking behavior or risk adverse behavior? And here for regressing on the median, we can see that the values are indeed different. However, they are not different by a lot. They're actually very close to those obtained, again, to that paper that we're using as a reference. But we can actually see that some of the behavior has changed, where we still see some of the stopping points for, again, the about 10 trajectories. Close to the beginning, some of them decide to go ahead and continue to do some more of exploration towards the end. But again, the goal here being, what happens if I start switching that alpha value? So if I start decreasing that alpha value, this is what will be considered a more risk adverse approach. And I can see how the values are now starting to look more like different, or they're starting to divert from the reference point. And what is more interesting is to sort of like see the plot, where I can see the trajectories here. I can see that there is actually, if I follow this pink, I can see that I would have done a lot better if I had waited, and I have just kept going and waited till the end. And that is basically what this sort of like risk adverse approach of the Quantile reflect, that I'm more hesitant to go and explore. I rather just do it now and sort of like call it quits and perform my action, do my optimal stopping, or decide this is my time to stop, as opposed to go ahead and continue exploring. And on the other hand, if we are looking for a risk-seeking approach or a alpha value that is higher than 0.5, we can see that again the values are very different for some of the instances when compared to that paper that we're using as a reference, that article. And if I look at the plot, I can see that most of my trajectories, they decided to just go for it. They just keep going, even though they might not have yielded the best results. I can see these guys above the cutoff line. Those are not, in this case, they're not good. They should have like basically call it quits earlier in the year. But some of them, I can see that they decided to continue explore it and sort of like move forward. So this in a sense sort of like reflects what I will say. Okay, let's be more risk seeking. Let's try and see what happens. Not with the best results in that case. But in conclusion, the results follow from those obtained again by Longstaff and Schwartz. That is the article titled "Value in American Options by Simulation." That is the paper that was sort of like the reference for comparing the results that were obtained in this using this approach. And what is interesting is to see that the median performed very similar to the approach to the mean, and also the mean, and for both approaches, for using the gradient boosted on the squared error, the mean square error regression, that one worked very, very close, which actually says that, hey, this is a valuable option. Now, the alpha quantile is interesting because the goal with this is, can I, instead of modifying my formulation of my stochastic differential equation, can I just play around with the regression algorithm that I'm using and modifying that alpha, the quantile, depending of where I want to be more risk adverse or more risk seeking. So that has basically was the motivation of this, is can I not touch the problem? Can I instead just play around with my regression approach? And gradient boosting regression finally benefits from GPU acceleration for training. So that is one of the biggest benefits on these machine learning approaches, that you don't have to sit around and think about the basis of your function that you're going to be using to fit that regression, the degree of your polynomial, and all these different things. You let the machine learning algorithm sort of like decide that for you. Now, in my specific case, I have a GPU that is an AMD. So I use ROCm's own XGBoost library for this. There are different options for different GPU support is also growing, so it's more and more being feasible and sort of like possible to do these approaches. But yeah, that's about everything I have. I hope you enjoy. Thank you.